Up until this point, we've said that vectors are free to float around in Cartesian space. We said if we had some vector, for example, if this was my vector A, we've said that it's not locked to a specific position, but it's able to exist anywhere in our Cartesian space. So it could exist down here, or maybe it exists up here. And we know that this is true because a vector simply has a direction and a length. Nothing in the information that is contained within a vector tells us about its position. It only tells us the direction and the length. However, sometimes it can be useful to lock a vector to a specific position in space. And in order to do that, we can introduce a special type of vector that's called a position vector. So we can introduce a special type of vector, which is called a position vector. Now, it really is important that this is the special case of vector. That means if someone just says, I have a variable and it's a vector, they mean it's one of these types of vectors. The normal vector that's free to exist anywhere in Cartesian space. All it contains is a direction and a length. However, if they have one of these special kinds of vectors, if they have a position vector, they should explicitly state that this variable is a position vector. So if you're reading mathematical texts, if they tell you you just have a vector, that means it's free to float around. It's just a direction and a length. However, if they tell you you have a position vector, then it's one of these special types of vectors. Now, the reason these vectors are useful might not seem apparent at first. However, some of the more powerful things that we can do with vectors do require them to be fixed to a certain position in space, and we're going to see that later in this DVD. So what exactly is a position vector, and why does it allow us to lock things to a certain location in space? Well, a position vector has a very special property. We know a vector has a start point and an end point, but because a normal vector is free to float around our space, those start and end points aren't defined. They're free to also float around our space. The only thing defined about that start and end point is the relative distance between them and the direction between them as defined by the vector itself. However, a position vector actually restricts one of those properties. It restricts the start point because a position vector always starts at the origin. So a position vector will always have the start point at the origin. And this actually gives us a very useful property, because if we know that a vector starts at the origin and we know it travels in a certain direction for a certain length, that allows us to define a particular point in space. And here's what I mean by that. If I had a point in space which I could name as capital P, so this is a point, and we know this point in space has some components. For example, if I was to draw a scale here on my diagram, we could maybe say that this is 2 in y and 2 in x. So we could say this point has the coordinates 2, 2. Now if I had a vector that travels from the origin to this point, and if this was just a vector that we could call A, we know that A is travelling 2 units in x and 2 units in y. So we know that A is the vector 2, 2. But notice, if we explicitly say that A is a position vector, that means A must start here at the origin. And if A starts at the origin, notice the correlation between the components of the vector and the point in space where the end of that vector will lie. They're the same, and this makes sense. If we have a vector that travels 2 units in x, and we're travelling from the origin, we know that we're going to reach an x-coordinate of 2. So if we're travelling 2 units in x, our x-coordinate's going to be 2. Likewise, if we have a vector that's travelling 2 units in our y direction from the origin, we know it's going to reach a y-coordinate of 2. So if we're travelling 2 units in the y direction from the origin, the y-coordinate is going to be equal to 2. So this allows us to say in general terms that if we had a point in space as defined by x1, y1, so the coordinates of the point, as I struggle to find the word there, the coordinates of the point are x1, y1, a position vector can define that single location in space because it's the vector with the components x1, y1, and because it's a position vector, and again, the mathematical text would say we have the position vector in English A. That means that A is a position vector. We know that it starts at the origin, and that allows us to know that however far we travel in x is going to be the x-coordinate of the end of our vector, and however far we travel in y is going to be the y-coordinate of the end of our vector. So a position vector allows us to define an explicit location in space. So there are two sort of important factors there, and I will recap over these. The first is that a position vector is a vector that's locked to a certain location, unlike normal vectors that are free to float around. And it's locked to a certain location because it starts at the origin. It always starts at the origin. That is the very definition of a position vector. The second useful thing to note, and this is a direct result of the fact that it starts at the origin, is that the components of the position vector define a point in space that is the endpoint of that vector. And that's because if we travel x1 in x, the coordinate in space of our endpoint is going to be x1. If we travel y1 in y, the coordinate of our endpoint in space is going to be y1. But why is this useful to us? Why is this so powerful when we're working with vectors? We can't really get into the true power until later on in this DVD, where we start looking at some more complicated problems. However, we can recap something that we've looked at previously. Because if you remember back when we were looking at the magnitude of a vector, and I talked about how it was similar to finding the distance between 2 points, and then I showed how we could find a vector that travels between 2 points. And we looked over that quickly, but I mentioned that there's actually a mathematically rigorous way to find a vector that travels between 2 points. Well, that mathematical rigorous way finds a vector that travels between 2 points when those points are defined by position vectors. So allow me to get rid of my units here, because we can deal in different units for this example. And I'm going to clear my diagram. Now I am going to show this using numbers to begin with, and then we can use more generic terms later on if we feel it's a necessity. So if we're trying to find a vector between 2 points in space, so let's say I had a point in space here, and this point was S, our start of our vector that we're trying to find, and this point has the position, I don't know, 1, 2, let's say 3 in X, and 1, 2, 3, 4, 5, 6 in Y. So 6, 4, 2, and 2, 4, 6. Hopefully that should be enough. So we have a point that's going to be the start of our vector, and that's going to be 3, 6. And then we have some other point in space. So, I don't know, let's say 6 in X and 4 in Y. And I'm going to call this point E, because it is the end point of our vector. So we're trying to find the vector that travels between these 2 points, and we could call this vector V. So we're trying to find some vector, it travels between 2 points, and we saw how we could do this in that earlier video, but we didn't really see the mathematically rigorous way of showing this. So the mathematically rigorous way of finding the vector that travels between those 2 points is to construct some position vectors for our 2 points. So we could construct a vector that's a position vector, so it starts at the origin and travels to our point S. Now the convention here seems to be that if we have a point with a capital letter S, then the unit vector would be a lowercase letter s, not a unit vector, a position vector, sorry. The position vector would be a lowercase letter s, but denoting that it's a vector. Likewise, we can find a position vector that goes from the origin to our point E. Again, the convention is to take the lowercase letter of the point and use that for the variable name of our vector. So we have 2 vectors. We have a vector S and a vector E. Both of these are position vectors, which means we know they start at the origin, and that also means we can easily find the components of both of these vectors, because we know if it starts at the origin, then the components are going to give us the endpoint of the vector, which is exactly how we're defining these vectors. We wanted a vector that goes to the point S, so that means the components of our vector S are going to give us the coordinates of point S. So we have 3 in X, 6 in Y. Again, if we start at the origin and we travel 3 units in X, and then up 6 units in y, we're going to get the endpoint of our vector, and we know that that is our point S. And our vector E is going to give us the coordinates of point E, so it's going to be 6 in x and 4 in y. So what we've got a vector that's going from the origin up to point S, and we've got a vector that's going from the origin up to point E. But what I want to find is this vector v. It travels between those 2 points. How are we going to do that? Well, what I need to effectively start at this point and travel to this point. Well, what if, and we've seen this when we were adding and subtracting vectors, what if I started at this point and travelled down to the origin, and then travelled back up from the origin to point E? If we did that, we'd still be starting at this point and ending at this point. So how can I express that in terms of S and E? Well, I need to start at this point, I need to travel down to the origin. So what I'm doing is I'm travelling along the length of S, but I'm travelling in the opposite direction, because S goes from the origin to that point. I wish to start at that point and go to the origin. So I need to go in the direction of minus S. I need to travel down in the opposite direction of S. Once I've got there, I then need to travel along the direction of E. So minus S plus E. This is going to give us the same as starting at point S and travelling to point E. Again, we've seen this when we added and subtracted vectors. So I've started at this point, I've travelled down to the origin, then back up, but that is the same as starting here and travelling directly there. So this is equal to our vector v. So if I was to rewrite this, I could say v is equal to E minus S. Notice how similar this is to when we were working it out but not using a mathematically rigorous version. Because when we were using the 2 points to find a vector back in the magnitude of a vector video, notice that I said we always take our endpoint and subtract the start point from it, and that will give us the components of our vector. Well, here's why. Because when we write this in terms of position vectors, our vector v is equal to the endpoint minus the start point. So now we have this simply in terms of a vector equation, and we know our 2 vectors, so we know that v is equal to 6, 4 minus 3, 6. So v is going to be equal to 6 minus 3 is 3, 4 minus 6 is minus 2. So our vector that travels between those 2 points should be 3 in x and minus 2 in y. So if we look at that now, we should be travelling 3 in x. Well, we start at 3 and we travel over to 6, as that line was a little bit off there. So we travel over to 6. So we have travelled 1, 2, 3 in x. So our x component is right. We started at 6 and we travelled down to 4. So we've travelled down once, twice. So we have travelled minus 2 in y. So by using position vectors, S is a position vector and E is a position vector because they start at the origin and they explicitly start at the origin. We can define these 2 points in space, and then we can express V here in terms of a vector equation that allows us to travel down S in the opposite direction and back up the length of V. So to find a vector that travels between these 2 points, we have found the vector V by using 2 position vectors. So again, E and S are position vectors because they are locked in space. They start here at the origin. However, V is not a position vector. V is just a vector. It can travel, well, it has a specific direction and a specific length, but it can be located anywhere in space. Why can it be located anywhere in space? Because it's just a vector. Again, position vectors start at the origin. We're not saying that V here is starting at the origin. It's just starting out in space. Now, we can get into this a little bit more, and we will see this later, how we can lock V in space if we refer to V starting from the end of a position vector. But that's getting a little bit further ahead of myself, and actually we're going to see that later on, much later on, when we define lines by using vectors. But for all intents and purposes, as we've seen in this video, remember that S and E are position vectors because they start at the origin, and only those two vectors in this case start at the origin, so only those two vectors are locked in place. V is free to float around our Cartesian space. We've just used the relative distance between our 2 points to define the direction and length of V. So with that, that's everything I wanted to cover in this video. I'm going to set one test question really to see if you understood the concepts at hand, both in terms of position vectors and how we can use position vectors to find a vector that travels between 2 points. So I'm going to bring up a new layer, hide out everything that we did there, fantastic, but keep my axes, and I'm going to define 2 points in space. And this point is going to just be A, and it's going to be, I don't know, let's say 2 in X and 7 in Y. And this is going to be my point B, which is going to be 8 in X and, I don't know, 3 in Y. And I'd like you to find the vector here, the vector V that travels from B up to A. So this is question 1. It's the only question of this video, and question 1 is to find the vector V that travels from B up to A, and I'd like you to do that in terms of position vectors, just as we saw a second ago on the whiteboard. So go ahead and pause this video, give this an attempt. If you get stuck, or once you have a solution, unpause the video and I will work through the answer here on the whiteboard. Okay, welcome back everyone. So as we saw a second ago, what we need to do in order to solve this is to construct 2 position vectors that define the points A and B. So I'm going to construct a vector from our origin up to point A. This is a position vector, that means it is going to be locked at the origin, and I'm going to call that vector A, and we know that A has the components equal to its endpoint. So its endpoint is 2 in X, 7 in Y, so it has the components 2, 7. I'm then going to construct another position vector, this time to point B. I'm going to call this vector B, and we know that vector B is going to have the components equal to its endpoint, so it's going to have the components 8 in X and 3 in Y. So we have our 2 position vectors. I'm explicitly stating that these are position vectors, and that means that they are locked starting here at the origin. So if we have these vectors, how are we going to define V in terms of these 2 vectors? Well, again, V has to be equal to the endpoint minus the start point, so A minus B. But let's see, if we weren't familiar or couldn't remember this, let's see how we could clearly get this from our diagram. We want to start here at point B, and we want to travel to point A. That means we need to travel down B, the vector B, but in the opposite direction, so minus B. And then we need to add on to that, because we've got to the origin at that point, we need to travel up A in the correct direction, so we need to add on to that A. So we'd have minus B plus A, which we could arrange to A minus B. So once again, that means we're traveling down B in the opposite direction, then up A in the correct direction. That's the same as starting at B, traveling to A, and that's going to give us our vector V. So that means we can find our vector V in terms of our 2 vectors. So we're going to have our vector 2, 7. I'm going to subtract from that 8, 3, and that's going to give us the vector, well, 2 minus 8 is minus 6, and 7 minus 3 is 4. So we're going to have the vector minus 6 in X, 4 in Y. We can verify that now. If we start at 8 in X and we move to 2 in X, we do need to move 6 units in X to get to 2 in X, because we start at 8. If we count down 6 units from 8, we're going to hit 2. We start at 3 in Y, we need to get to 7 in Y, so we do need to move up 4 units. If we counted up 4 units from 3, we would get 7 in Y. So this is our final vector. It's minus 6, 4, and that vector was defined by using 2 position vectors to define these 2 points in space. So hopefully you followed along with that okay. If you didn't, then just rewatch over what we've covered in this video so that you fully understand the concept of a position vector. Again, a position vector is a special type of vector where we're explicitly saying that vector starts at the origin. Then make sure that you understand how we can use position vectors to define points in space. We know that if it starts at the origin, then the components of the vector are equal to the coordinates of the endpoint. And then make sure you fully understand how we can use 2 position vectors to define 2 locations in space. And then we can use vector addition and subtraction to define the vector that travels between those points by traveling the negative direction of one of the vectors and the positive direction of the other vector. And that's the same, of course, as traveling along the length of the vector we're trying to find. So with that, that is going to conclude this video. Thanks a lot for watching, everyone.